Makerere Nathan, Group 49. Our project is an autonomous self-driving wheelchair for inclusive mobility at Makerere University. These are our keywords, and down there is my colleague, Namganza Isabella. These are the contents we have to deliver on the background. We all know that limited mobility among persons with disabilities at either Makerere University or other university, other schools, and Ugandan health facilities lead to dependence on escorts, delays, and inefficient staff utilization. So we know very well that currently the wheelchair which are being used require manual control, even someone to push like an escort. This limits independence, especially in crowded or complex spaces. Recent advances in computer vision, AI-based navigation, and the low-cost embedded systems have made it easy or possible to design autonomous mobility aids. This project is going to use these technologies to create an affordable self-driving wheelchair for inclusive mobility within Makerere University, and of course beyond. The goal is to enhance accessibility, safety, and independence for students and staff with disabilities. Here, we are going to use technologies, features, or you can call them the components. And one of them is going to use the sensor integration, or you can call it sensor fusion. The sensor fusion is going to combine the RGB-D camera, the light detection and ranging, you call that one LiDAR, and the ultrasonic sensors, plus the IMUs, the inertial measurement units, for accurate environment perception, that inertial environmental units, perception, and wheelchair stability. So we have also the mapping in technology. We have mapping, which is uses SLAM, that is the simultaneous localization, and mapping to create and update the real-time map for university corridors, pathways, and so on. So you also have planning. This wheelchair must be having a planning system inside it, whereby it employs the graph-based algorithm, that is the ESTA, to compute the safest and most efficient route to destination. You have the obstacle avoidance or detection. That one is powered by the YOLOv8 and semantic segmentation. So we also have the hardware optimization, which will be running efficiently on the low-cost NVIDIA Jetson Nano. That is a low-cost computer. We also have the interface, which we may be using either a mobile app or a mounted on screen, which will be on the wheelchair. Now the goal is to provide a scalable, low-cost, and inclusive mobility solution, empowering persons with disability and promoting independence at Makerere University and other health facilities. So you have there the sensors, which will combine the camera, ultrasonic, IMU, Jetson Nano, which is embedded this system for a computer, whereby the system is going to be run on. And we also have the wheelchair itself, which will be comprising of the chassis, motors, and the controls for forward, turn right, turn left, and the stop controls. So that's the introduction and background for it. Now, before starting on this project, we had researched about other related projects and papers which were done in line with our project, and we found that Morgan Study AI, those one developed a wheelchair by using the robot operating system and CNN, that's a convolutional neural network. This one, it was working very well and was to be employed in the airport. So it is even in use as per now. It is being used in airport for self-automation. So it is using manual and the self-automation, so it can move very well in the airport. But the reason why you didn't adopt it, it is complex and they need high-end hardware, which are expensive. So we also have the Michigan Conv system. This one used the sensor fusion that is smooth and so on. So it was designed and it was designed working well, everything was smart, but it's not for low cost settings like Uganda here. Now when you got this it AI, the one who used the generative attention network and the relational generative convolution network, this one was excellent and it was planning everywhere, everything well, but it requires a large amount of data in millions, which we can't afford at this. And even though we are to afford, it means that it will have to run on an expensive hardware, which will not be sufficient for Uganda setup. We also have the Billy. These guys, they also employ the YOLO as we are using, and also SLAM. For them, their performance was also okay, but it cannot perform well on low powered devices like what we are having ours, which is in NVIDIA Jetson. It can't. So we also have the VINs. The VINs, they used the neurosymbolic gun. This was very perfect and so on, but the system was too complex. To beginners like us, we even lacked where to start from, but we still adopted some technologies and some ideas from them. But also not being complex, also it cannot run on a low power device like NVIDIA Jetson, and also complex to design, meaning it can be too expensive for Ugandan setup. Now here comes to ours, which is Makerere University 2025. We are employing YOLOv8, the A-star algorithm, and simultaneous localization and mapping. We aim at simplicity and cost effective. Of course, it may not be good at the beginning, but we shall be improving, and we commit to be improving it every now and then. Yes. From there, we got the problem statement. The domain specific, these are the real life problems. We have dependence. You know very well that students need escort for basic mobility. That is, now look at the delays. Someone waiting for 30 to 60 minutes during the peak hour, that's morning, evening, or even lunch hours. That's too frustrating. Now also the discomfort, navigating the crowded areas and uneven path is very hard, and it can even cause some collision sometimes. So computation problem, we have perception. How can a wheelchair see and understand everything around it? Mapping, how can it make a map to locate where it is, and also move smoothly to a destination without using a GPS inside. Planning, how can it really plan a safe and shortest path to the commanded destination, like from library to lecture room A or B, like that. So obstacle avoidance or object avoidance, we have how can it really move safely, avoiding obstacles which are dynamic like people, and even maybe static objects like walls, trees, and so on. So, and finally, how can it really run on AI low power computer? Because we want to be all these AI systems, from perception, mapping, planning, and object avoidance, combining them and running it or running them on a low power computer, NVIDIA Jetson. Those are computation problems over here. The research questions we are asking: how can really a simple AI model enable safe navigation indoors? How can we really combine camera, sensors, and all data to avoid obstacles? Now, Another thing we say, can basic graph algorithm like just a mere star find a good path on campus, really without a GPS? Now, research objectives we have is to build a simple SLAM system for mapping indoors, to train a basic object detection model, that's the YOLO, to see objects, to implement path planning algorithm, that's the ESTA, and also to deploy and test the whole system on NVIDIA Jetson. Research contributions, we already designed and began to assemble a prototype of a self-driving wheelchair. We implemented preliminary SLAM and the navigation model. We started collecting environmental data around the campus, inside the campus and corridors. We tested AI models on desktop, preparing for deployment. Obviously, we tested the YOLO model, that's the object detection and avoidance model. That is it's done. Now, the system architecture, we already have the user interface layer, which you will be having the user input, where you can put the voice, text, or even you can use the graphical means. And we have the perception. The perception is to receive data from the environment, where you have the RGB-D camera, light detection and ranging, LiDAR, inertial measurement unit, or IMU, and also ultrasonic sensor. Now the brain will be having the YOLOv8 model, that is a convolutional network architecture design model. We have mapping, which will combine the simultaneous localization and mapping, SLAM, and we have the ESTA algorithm for graph planning, meaning planning the path where to go. Also motion controller, that is, will be having the model predictive controller, and also the Arduino controller for motors. We also have the DC motors, how they can move and so on. Then we also have the hardware base, where you have the wheelchair chassis, battery, and the LED. So that is the system architecture we are having. And the models, they have their mathematical background. The models we are using 3 models: object detection, path planning, and the localization and mapping. So on the detection model, we are using YOLOv8. What YOLO does, it finds boxes, it finds and boxes the obstacles, like the cars, the chairs, the trees, and so on. So the simple math, like, it looks at the image as a grid, and it predicts an object in each grid cell. So the box prediction, bounding box prediction, you will find that it will use the center points, which is the X and Y, width, height, and also the confidence percentage. And we also have here the path algorithm, the path planning, where you have the A star algorithm. What this one does is to find the shortest path from point A to B, like a lecture hall to a library. Now the simple math beneath it uses a cost function to pick the best next stop, whereby here we are having going somewhere, you have to add the cost of distance from node N to where you are going, and also the estimated, you are going to add the cost from start to node where we are going, where they are calling node N, that is the GN. Now also plus the HN, that is the estimated cost from N to a goal. You call it the heuristic, or other people, they call it the Euclidean distance, where it is N and to goal, from a distance N to goal. That's the formula for it. We also have the simultaneous localization and mapping. This one, it built a map and track the wheelchair's location in it, and at the same time, so it finds where it is and it maps where it is and where it's going. So It uses sensor data like LiDAR or ultrasonic to guess how the wheelchair has moved and update the map. So from there, this is from the pose, the map, and also the commands. The pose X, the map M, the command Z, to the equal proportional to this. So these are the let us maybe look on the architectural diagram for each model, where we can start with the YOLO. For a brief, the YOLO is having three sections, where you have the backbone, the neck, and the head. On the backbone, its work is to perceive the features on an object. Like if it's a human, where you have the nose, the eyes, the hair, the skin, and the structure, the whole, everything, it partition them and perceive them. Now it sends that information or that perceived data to the neck. The neck is its work is to perform the convolutional operation, whereby it will converge them, and now after analyzing, it will send to the head. Now the head, its work, it will only be to detect. It will be detecting. It will be to detect and also draw the bounding box on that object, and also classifying them like that. When you got the path planning, it will have the environment, where you have the environment, and this one is having the trees, chairs, and so on. And also you have the universal aerial vehicle. When you have also the universal aerial vehicle, this is our wheelchair now at this moment. And you also have the mission, whereby it's going, where it's going, and you also have the threat information, where this one is the longest distance, or the distance or the path which is having obstacles which you have to avoid. So that's the path planning algorithm. Now when you come to autonomous operation, we say, is it a human is intervening? If a human is intervening by saying, yes, I want to take this direction, it will obey and take it. But if you don't take, you don't dictate the direction, and you just tell it, I want to go to lecture room LLB, it means that it will have to figure on its own and execute that mission autonomously. When you go to SLAM, the SLAM, it is having three sensor data. You have the RGB-D and the IMU. You also have the LiDAR sensor data. So from here, I will not explain all these one. They are very self-explanatory due to time. And out of this one, you provide a 3D map, where this one, the 3D map, is the one which it has mapped, and it can locate exactly where it is. The data set, we are still collecting some data set from the college and annotating them. But due to that process being long to annotate, we have decided to go for the public data set from RoboFlow. That is the self-driving data set, over 800 labeled image. So from there, this is a graph showing like how many cars in those images, how many trees. You can see them, because it is a self-driving, you expect many cars and trees there, plus maybe the road and pedestrians. So from there, we also have the sensor data, where you have the LiDAR and the ultrasonic and LiDAR. This histogram says that if you are at 0 meter to the object, a wheelchair to the object in 0 meter, it means that you have knocked already. You cannot see anything like sensor data or a deflection on the LiDAR. But if you are a little bit far away, like on 1 meter, or between 1 meter and 3 meter, here we see 1 meter and 3 meter, we see that there is a high deflection. So if someone is at 2 meter towards the object, we shall see a high deflection, saying that there is an object in front, so stop immediately or look for another way where to go. So if you go near to it, you find that you are nearing to the object, and even this sensor may even sometimes fail to detect when you are near it, because you are just, they obstruct it fully. And another scenario is that if something, an object go beyond 5 meters, here we are seeing that even 4 meters, that you cannot detect the object. So there is a clear path when you are going in front, and it is a high maybe distance 4 to 5 meters and above, you'll be there will be nothing detected. Also the obstacle will be in front, but for it will see that I still have a degree of freedom. Yeah, so this was the explanation. When we go to the correlation matrix, we can correlate, like we are correlating two individual things. Like here we can say maybe the LiDAR distance and obstacle level. This LiDAR distance and obstacle level, we see here that it is a 0.075. 0.75, it indicates a slight negative link, as meaning as the LiDAR distance increases, obstacle really decreases. So maybe let us take the one for inertial measurement unit. When you got inertial measurement unit acceleration, it also say a tiny, very tiny positive link between them, meaning there is a change. There is a change in the inertial measurement unit as the obstacle appear. So they correlate. But where you cannot find any correlation is between a sensor and a sensor, meaning if you are making like a LiDAR distance and inertial measurement unit, you'll find that almost there is no correlation between them. So they can perform simultaneously together, like they can be together and perform simultaneously in a parallel way. Yes. So from here, this is the YOLO training. From the YOLO training, we find that this is the training box loss. So the training at first, it was at 1.4. But as the epoch increases, it means that with training, it keep on reducing the bounding box loss. So the box loss indicates that it is learning and it is going to detect accurately with a higher percentage. The same, the training classification loss, from 4, imagine a sharp decrease to almost 1.5, and finally it goes to 1. This means that classifying object, it is increasing in its confidence, meaning it was learning very well and everything is now perfect, it can learn. And now if we go to the gain, still the gain, if it's coming from 0 to 5, it means that it is doing what? Yeah, it is running very well from there. So these are the explanation for it. When we come to the confusion matrix, the confusion matrix, this one, it indicates very well that from a car, we are seeing here a car from here and a car, meaning these are the real cars, but there will be some outliers whereby instead of a car, you are seeing a road. So this one is just an outlier and it cannot like a sky road. Now even here, when you say trees here and here, meaning they are identified correctly. When you say roads here and road here, so this line which is now confusing you is the background. When you say the 214, they are in trees, but background, still the trees, if they are blurred, since the road is covered by vegetation, it means that there are many trees in the background, so it is okay. And when you see up here the cars, if the image is blur, it cannot indicate well that it is a car, so it can really just take it under the background, since there are many cars and they are in the background, which is fine. All this one become fine and okay. So the deployment, so deploying, we have to deploy it on Ubuntu, that is the robot operating system, and the interface, we have the TensorRT engine, that's the YOLO, and the latency, we have to be less than 150 millisecond end to end. On the power, we have to use on average like 8+ hours on a battery, which is 12V, of course lithium. The mobile app, we have to develop it in Flutter, and we put in the voice control, text control, or graphic control to the destination where someone say voice to the destination, and also maybe live map, and also wheelchair status, and also putting an emergency stop button either on the app or directly on the chassis of the wheelchair. And the problems, we experience the problem of data set, limited data set. There is a small data set, making it to be confused, and also it doesn't cover all scenarios like in the crowded corridors. To overcome this, we are going to do data augmentation and collect more advanced data sets around the campus, inside and outside. The model architecture limitation. YOLO model misses distant objects, and particularly hidden objects, and it can miss LiDARs, like as you saw on the outliers, although if they were small, but they can still be a scaling factor. On the system architecture, limitation is the slowdown, meaning we expected it to be less than 150 millisecond, but we know it can go up to 200 millisecond or above in delay. So when many sensors are connected and are working, we expect a delay. But here we have to overcome it by optimizing the code and apply threading for parallel sensor data processing. The conclusion, we successfully designed and started building a low-cost autonomous wheelchair. Our initial model for detection, that is the YOLO model, and path planning are working, although the working path planning and the ESTA algorithm are supposed to be on either simulated or the hardware. So we are now having the YOLOv8 model being worked on, and it is working actually. As beginners, we have a functional prototype or YOLO model and so on, but still there is a lot to be improved. In the future works, we expect to improve the object detection accuracy by collecting more data, as said later, test the complete system on a real-world wheelchair chassis and on campus, of course, and add a voice control feature to mobile app for easier usage. Explore how to make the system work indoors and adding GPS on outdoor usage. These are the references, and here we really take our appreciation to Mr. Gary Wangu, also all the college lecturers and the college at large. Also, we cannot forget the open source community, the robot operating system, the RPLIDAR, YOLO, and also our classmates of all. Thank you.